So I'm Malcolm Williamson. I'm with the Center for Advanced Spatial Technologies, known as CAST, at the University of Arkansas in Fayetteville, Arkansas. And I'm going to be talking today about geospatial perspectives of the built environment. So how do I look at all of this? And why should you look at it this way? In the beginning of my previous career, I worked in maintenance with Hiram Walker & Sons in Portsmouth, Arkansas, an automated warehouse. Back in the 1980s, we had robotic storage of 40,000 pallets. And we not only maintained, we designed and let contracts, and I was heavily involved with operations. So, where I'm working currently at CAST, we're located at the University of Arkansas. We're focused on research, education, and outreach related to geoinformatics and geomatics. In the early days of GIS, when I started there, this is 22 years ago, we used GRASS, which is open source software, which is back before it was popular, it's back out there again now. ArcInfo, which is command line driven software. We're outputting graphics to pen plotters. But even back then, we recognized the importance of topology, the idea of the connectedness of things. And we enjoyed the ability to have attributes tied to all this graphic data. We could ask questions about where things were and how they interacted with other things. And back in the early days of GIS, one of the big disconnects was importing 2D CAD data. And so this was a large enough problem 20 years ago that started at least one company, Safe Software, and they're still around today converting all kinds of data from one format to another. These days they do 3D data. We dreamed about true global 3D GIS, where we could model the entire world at whatever kind of detail that we wanted. We were also very aware that there were plenty of spatial questions that were not geographic in nature. We used the same tools and approaches because we saw no need to reinvent the wheel. So back in 1999, I was using a close-range laser scanner to scan primate teeth and using GIS software to model the wear and morphology of teeth. It's just a different scale, it's still the same type of problem. And then a few years later, we moved into the 3D reality capture world. We got our first landscape terrestrial laser scanner back about 12 years ago. And we've worked around the world at a variety of sites capturing data and using it for both preservation and analysis. So, back in 2006, our founding director, Fred Limp, was involved in writing an article that was published in a magazine then called Geoworld. And his concept was the idea that there were at least 3 different industries out there: gaming, AEC, and geospatial, that were all really trying to do the same thing. They were all interested in modeling the world with information about it. And so he talked about this, the idea that behind these massive multiplayer online games, these will change the geo world completely, and it'll happen soon. He's talking almost 10 years ago about this. Today, we're just now starting to see this integration, this crossover. Obviously, companies like Autodesk see this as they are moving into all these different realms. Microsoft, Google, we're all looking at all this same sort of things. So I'm going to be talking today about 2 key areas: reality capture, and then modeling, analyzing, and managing data from my perspective, from the geospatial perspective. And so first of all, I wanted to talk a little bit about sensors for reality capture. And we've got active light source sensors. So these are the mostly laser scanners. We've got time of flight scanners, such as those from Leica, Regal, Optech. These are basically like the survey instruments, where we're sending out a beam of laser light. We're measuring how long it takes to get back. These have the longest range and the lowest noise out of all the active scanners. Then we've got phase-based scanners, such as those from ZNF and Faro and others. These are fast. They are distance limited because they're limited to a single wavelength of light, wavelength of code on the light beam, and so they can't go beyond whatever that limit is. And then finally, we have structured light scanners, where you're using white or infrared light to provide a pattern that we're then recording with cameras. And these include things like the Kinect, but also high-end scanners like those from Breukman. These are, or can be, inexpensive, obviously, but they also usually need relatively low light conditions. You can't use things like the Kinect outdoors very effectively because the light's being washed out by ambient light. And then we have passive light sensors, those that are using available light, which is basically photogrammetry. And so we've got software like Agisoft Photoscan, Visual SFM, 123D Catch, Pix4D, and this technique is relatively inexpensive today. You know, there's really two primary steps in here. There's the big one, autocorrelation, matching points on images automatically, and that is really what makes this software possible. And I don't know how many of you are aware of the algorithms behind this. SIFT was really the magic algorithm that made this feasible on large scale. And then we're going to densify the surfaces between these correlated points, and then at some point you've got to introduce scale, because photogrammetry by definition does not know how big things are. It doesn't know if you're, you know, close up to a little model or a long way from the actual item. Of course, we've got to deal with cumulative error in photogrammetry. Is usually the biggest problem is if you're covering a large area and putting these photos together, you get drift, and you've got to have some way of correcting that out. No matter which approach you're using for reality capture, you've got three different criteria to keep in mind. You've got accuracy, you've got precision, you've got resolution. Accuracy is, you know, the ultimate, how close am I to where it really is. Precision is basically repeatability, but more commonly in 3D capture, what precision really reflects is noise. If I'm measuring the same thing more than once, does it show up, is it in the same spot? And we want things to look like they do in the real world, so we're just as concerned with precision as we are with accuracy. And then finally, resolution. What's the smallest thing I can resolve, which is really what's my spacing of my measurements. And so, you know, the bottom line is we've got three different things to consider in reality capture. We've got accuracy, we've got speed of capture, and we've got cost. And basically you pick the two that you want. You can never really obtain all three of these. You can get good accuracy at high speed, but it's going to cost a lot. If you want speed and don't want to spend a lot of money, your accuracy is going to suffer. Or if you want accuracy and you don't have a lot of money, then your speed is going to suffer. So it's all kind of a balancing act there. And so now I want to show you some examples of things that we've been involved with, and kind of talk about how this pertains to AEC. And so this is just a little overview map of our campus. I'm going to be talking about a couple of projects. The two upper red buildings, I'm going to show you some scanning work we've done there during a restoration project. And then the two buildings in the lower part, those are actually our heating and cooling plants on campus, and we've done some building modeling there as well. So first off, I'm going to show you some examples of where we've worked in some pretty intensive environments, modeling buildings for the group that's known as the physical plant on campus. We are helping them model a building in preparation for bringing a new boiler on campus. So we, working with an engineering firm, we basically asked for the opportunity to collect this data just to have some practice in this particular area. And the understanding was that they would take this data and the point cloud data and then model it, bring it into CAD formats so that they could actually then, you know, see how much clearance they had, see what pieces need to be relocated before bringing this new boiler in. But we approached it from our kind of the same approach that we've used in heritage scanning. We said, you know what, let's get as much data as we can. So we went in there and scanned the heck out of it. Many different locations, high density scanning. And so when we turned the data over to the engineering company, they looked at it and they said, actually, we can see everything that we need to see in the point cloud, and everything that we've got, in some cases, spacing of a couple millimeters on the points. Anything that they wanted to measure, they could measure, and so they ended up not bothering to turn it into CAD because they could do everything they wanted and save that time and money. We did do a little bit of sample feature extraction. These vents and these pipes here, we were modeling those. And then, so basically, this data was also turned into a series of floor plans showing where the equipment was. And we delivered it also in using Leica's TrueView Platform, which is a web-based plugin that allows you to look at the data from the scanner perspective. So basically, each, on this lower corner down here, each one of those little yellow triangles is a location of a scanner set up. And as you click on each one of those, you get a view, as up here, where you can panoramically view around, but you're always looking at it from the perspective of the scanner. So you don't see the occlusions. You see exactly what you see. It looks like 3D photo, but you can measure between any of the points there with accuracy of a few millimeters across all of that in 3 dimensions. And so that's a pretty useful tool for the guys in the field. Then the second project I wanted to show you was a documentation project originally. There was a building, one of the older buildings on campus. It was the original library on campus. It had been used as the primary facilities for the School of Architecture, and they were going to do a pretty major demo and remodel on part of the building. And so we were going to go in there and originally just scan some of it before the demolition. So we went in there, did interior and exterior scanning, even getting on top of some of the adjacent buildings so we could get upper parts of the building during the pre-demolition phase. And originally the contractors kind of just felt we were in the way, and then one day they looked at some of the data and said, "Really? You can see that? Can you actually measure that?" And we said, "Oh yeah, look at this." And they said, "Do you think you could scan this as well?" And the longer they started working with us, the more they started seeing the potential. And so in the end, we ended up working in all the phases of the construction. So pre-demolition, and then during the construction phase, we scanned before they put the sheetrock and the ceilings and the floor tiles down so that we could see all the MEP. They asked us to scan the post-tension cables prior to actually pouring the concrete. When they said, "Could you scan those where we could actually see where they are after the fact?" And we said, "Sure." And so instead of having to hire, someone with an X-ray machine or GPR to come back and find the cables down the road, they can go back and look at this data and measure precisely where they are and say, "Don't cut here." And then we scanned after they covered everything up. So when the building was finished, we got the whole thing. So one of the potentials that we see, and I think this is a great project for the hackathon down the road perhaps because it's pretty complex, is we've got great data. How do I create an app that can locate myself accurately enough in a room that I can then know where I'm looking on my tablet or my phone and see the data that's behind the wall or the ceiling coverings? So that's a big deal, but you need to be pretty darn precise in your location to do that. And so here's some samples of the data of that building. This is several billion points in this data set, and you can take slices, dices, turn on different phases of construction and see all of it. This is looking inside one of the rooms pre-demolition here, and then during the construction phase. And then again, here are some of the deliverables that were produced off of this: floor plans, tying in cross sections, showing the ductwork and piping above the ceiling there. And one of the things that we've actually also been talking to some other researchers about is putting in a sensor network in this building and some others that would be using very low-powered sensors that can actually be powered by energy in the environment. So there's a professor that used to be at the University of Arkansas, is now up in Maryland, who's done research in this area where you're either using heat, ambient heat to power the sensors, or light or air movement. And so basically you tie the sensor data into this very accurate as-built model. You can really start to use that to analyze the environmental conditions inside this and see if it's actually performing as planned and make the changes appropriately. Now I want to jump and just kind of wrap up some thoughts about where are we with BIM and where are we moving forward with all this. So in my mind, what we're really talking about is building information modeling, analysis, and management. Okay, it's not just modeling. The analysis part is perhaps the part that we don't do enough of. Management, there's a lot of folks out there that are very interested in that. And so, borrowing this table from the Computer Integrated Construction Center at Penn State, this is looking at all the phases that they identified where BIM could be used. And so 4 major headings: planning, design, construction, operation. Let's look at some of these and think about, are these geospatial in nature? So in this planning, we're looking at site analysis and existing conditions modeling. This is definitely going to be using geospatial data. We care about where it is. We care about the environment. We also are going to be looking at, in the design phase, we've got all sorts of analysis. We've got structural analysis, lighting analysis, mechanical analysis. And so some of that's also going to be considering the environment as well as the interior of the building. And maybe thinking about macro and microclimates as well. And finally, construction, we obviously need to know about the site conditions. And in operation, well, everything in operation is about where things are. So the geospatial nature of data is essential in thinking about BIM. And if you think about the life cycle of a building, so we're talking about 4 years to plan, design, and construct an institutional type building, 50 years to operate it. So 93% of the life cycle is actually dedicated to operation. So again, when we're thinking about BIM, it should be building information management and analysis. That's really the big part of it, is what do you do with the data? What can you do with the data? And I like this quote. This is actually from Dale Lutz, who is, remember the company that got started converting CAD software to geospatial software and vice versa. He's their CEO, and he says, BIM is, he quoted an audience member that BIM is really an information model about a building, not a building model with information. So I think that's really the key to getting the utmost utility out of where we're going with all this technology. And of course, one of the keys to all of this is talking about level of detail. These guys here, this is the BIM forum, they call it level of development. It's the same concept, same name, LOD, right? And so, this is one of the things that really, we all need to agree on. We all need to agree on the level of details, and we need to make sure that we get down to enough detail that we see, we have the potential for seeing everything, for modeling everything. Because sooner or later, we may not be doing it right now, but sooner or later we're going to be modeling, every outlet cover in enough detail that it can be manufactured at some point. If we're not, we're silly. And then I wanted to wrap up by showing some work that some of my colleagues have been doing on campus. Kind of a little different variation of BIM, not so much the definition, but the same idea. You've got 3D models, you've got data, what can you do with it? So in this case, they started out with what they call their room use survey, where they've gone around and every model on our campus, which is pretty good size. We got 26,000 students. They know, how big is it, what department's responsible for it, how many occupants are in it when they visited it, how many seats are in there, what's it used for, and then what is it being used for at other times. This can also be tied into our student database. We know the room number. We actually know not only how many students, we know specifically what students are supposed to be in that room, what time of day, which if you think about disasters and things like that could be very valuable information. So we've got this traditional database. We've also got CAD data. So the university, of course, has detailed 3D CAD data of every building on campus. So if you got these together, what can you do with it? Well, let's start by driving some 2D spatial analysis where we can create 2D maps that taking the information in that database and attaching it to simplified level of detail data from the CAD drawings, and we can see what each of the rooms is being used for at a particular time of day. So we've got the 2D version of the data, and so we've also got elevation data for the campus, quite nice data from our local city, and we can use that to then set base elevations for all the 2D data and extrude our buildings as simple sugar cubes, but with the rooms included and doing it level by level of the buildings, tied into the database, and now we've got 3D visualization of where the people are, where the uses are across the entire campus. And this can, of course, be put on the web, and it can be updated live. If you change the database, the data changes. This is what's readily done today. So that's kind of, I hope, the direction that we are all moving. We've got lots of data. We've got lots of good geometries, and getting it all tied together to use for all these purposes, including fabrication, I think is the the key to getting the most out of our money. Any questions?